I worry, am I doing the right thing now? To be able to get her, and I think and I've moved quickly, so it's quite numbers and now changes. So you go, there's two ways, or you could try or in this country, yeah, you have to specialize. I mean, not always, but that's how it's going to work. Yeah, I say I'm quite the way at the moment with how to as well, I think it's stressful at the moment. Compared to at home life, where I think everything like I'm good. So I say to myself, I should stay here, but I can't. My friend. I think this is also true. I think this is not really matched. Yes. And I think again, you should. And you feel that issue, like you can say, yeah, that's Especially this year, so I say that and enjoy that.
My mum does, she swears by us. It's just because we're your ball, but she's. No, just separate.
What's your Aries?
Yeah.
You know, like you see a lot of time when you're now, she's
Step 6.
How much was my really? How much range?
Oh, no.
Don't worry about the range. If I have this money.
That still wasn't enough, and he decided to become the governor of California.
Is he still? Yeah, it's not. It's not. No, now it's Houston, isn't it?
Yeah. Used to be Eastwood, so they go.
Yeah, they just changed that.
Yes.
Stars.
Yeah, that's what they do.
I know.
You know, what I was going to say was that's what I expected it was.
Yeah, you don't have to be born there.
Because for a president, have to have been born
Like
in
it's like,
American
it's
soil.
not saying like, you have to like,
Yeah, you can. You can be part of the Senate. You can also be part of the state representatives. You need to be American.
Okay. So you, or you can just skip that and just become a CEO of BlackRock. I'm amazed to say like billionaires
they don't give me a question.
No, I guess it's more about like it makes
Oh, yes.
That's hard.
16.
His first fight got cancelled, so he's like, if you still want to come and see me, I appreciate the support. There's no way I can let myself get embarrassed by using
We've got like only one
It's not
yeah, but not I've got minor.
Everyone knows what I would know. You guys all just sidetracked from onto my story. And then we see
so big for everything.
Mid-work, yeah.
Like for everything.
I don't know.
Mr. Peter, what is your
Just Peter. Yeah.
Dr. Peter?
What?
No, yeah. What's your personality type? You know.
According to my wife, difficult.
Good answer.
What did you expect? What's your personality?
We were talking about careers. The conversation came up about how your personality should match the job that you're doing in theory, or if you'll know what you like about that job and what you don't like about that job. It's dependent on your personality.
What happens if you've got multiple personalities? Can you have different jobs then?
I like that. That's a good one.
Yeah? Yeah? Shall we make a start? Yeah, then we can hopefully go a little bit sooner, and I hope you don't mind that. Okay, let's get started, and welcome. Well, I can't say welcome back because I've been away. You haven't been back, or you haven't been away. So what I want to do with you in the last few sessions is actually talk to you about how we also analyze discrete data. So far, we have exclusively focused on continuous data. And this is a very, very common data format that you will encounter, for example, biomarker, height, weight, age, whatever. But there are also, of course, other types of data where we don't have anything physically possible between two adjacent measurements. I gave you the the idea of, for example, number of people in the room. It can't be a fraction of a number unless you are willing to count pregnant people or something like that. But we don't want to do things in this respect. And you can immediately think of discrete data. For example, you all have worked with discrete data when you, for example, look at Amazon rating. You can give 1, 2, 3, 4, 5 stars, but you can't give 4.5 stars. Or in this case, you can't give 0 stars, which hacks off a few people. If the service is so loud or the product is so lousy, they want to give 0, but they still have to give 1 because that's what the system only allows. If you look, for example, at pain levels, very often you have this Likert scale type data, Likert scale, because a guy called Likert invented that with this 1, 2, 3, 4, 5 or something like that. And so people might ask you, how do you feel today on a scale of 1 to 10? And you usually would not say, I feel 6.348. You just say, I feel pretty shit. So it's let's give it a 2 or so. So this would be discrete data. And what we are going to discuss are basically sort of a handful of different scenarios, if you like. And the first one, probably the easiest one, that fall into this discrete data set is count data. You might say, can you have something else that you don't count? Well, this is the official name. So we are looking at count data and rates. And count data, as the name says, it is we count occurrences of an event and then try to analyze that. And we also have a sort of how this data occurs. What this rate means, it means per time or per space. So, for example, a classic example is people clicking on a website. You count people, or you count the clicks, how often a website is called. And that would be the number of hits in a certain time frame. In, for example, a week or something like that, bless you. And then you sort of try to figure out what's going on. Is there something unusual going on? And we can actually use exactly the same concepts that we've discussed for the continuous data for these count data. And I mean, there is a sort of, bless you, there is an interesting sort of, there's an anecdote from the Ornithological Society of Norway, who have several years ago, who set up a website about bird watching in Scandinavia. And that website got about 5-6 hits per day. And that would be a typical rate, 5-6 hits. You can't have 5.5 hits because it's not defined, so 5-6 hits a day. And then they had a sort of a promotion, and they discovered that within an hour after launching this promotion, they had 12,000 hits. So, you know, they asked themselves, what happened? So what they did was, first of all, they said, is there a difference between what we do usually and what we have done in this case? This is actually called A/B testing. It's either A or B. And they did some analysis. In this case, you don't have to do a big analysis. There is very clearly a difference between 6 hits per day and 12,000 per hour. So even somebody who doesn't know how to do statistics, they will find out that, yes, there is a significant difference. And yes, obviously there was. So they tried to figure out what happened. And what actually happened was they launched a sort of an initiative that got these hits, and they called it watching tits and birds in Scandinavia. And of course, that attracted a lot of attention, but probably not people who were interested in bird watching. There were, but that is an example of where we compare different rates with each other. And the statistics or the distribution that I want to discuss with you under the count data, we assume that these data follow what is called a Poisson distribution. Indeed, Poisson is the French word for haddock or something like that, or fish? It's just fish. Okay, yes. It has nothing to do with fish, actually. It was just invented by a French person called Poisson. Who basically came up with this idea. And that's why it's known as a Poisson distribution, where we look at these rates. Another example of a rate would be, for example, would be colonies of bacteria on plates. That would be not per time, but per space, where you say you've got 15 bacterial colonies on a plate, and you might have another plate where you have 20 colonies on a plate, things like that. And very often we will find that these counts follow a Poisson distribution. And you can analyze them with this Poisson distribution. The Poisson distribution has a few characteristics, like when we set the normal distribution, we have to make some assumptions, or it has to meet some criteria. For example, typical for a Poisson distribution is no two events or no two counts can happen exactly at the same time. Exactly at the same time. The events must be independent of each other. Events independent. So, example with a website, you should not have people saying, hey, we are now clicking on the same website, all of us at the more or less at the pretty much at the same time. So it needs to be some independence there. And the rates must be homogeneous, as they say. Over time or space. The last one is usually that causes a little bit of anxiety when people hear that. It means that the same rate must, in theory, be possible for all the events that we are looking at. I know it all sounds incredibly abstract, so I'll give you an example for a typical Poisson distribution. Oh, I also need to say the Poisson distribution can take any value in theory between 0. You can't have negative events. That's not possible. Between 0 and, in theory, infinity. So there is no bound to the, to the infinite side, to the big side, but there is a bound to 0 because it can't be negative. Classic example. We want to know how many people are actually using the toilet in a pub. And why would we want to know that? We want to know, for example, do we need to install a second, a third, a fourth toilet, or is what we have, is that enough? So we want to figure out how many people use the toilet. And what we can do is we just simply have somebody sitting outside the toilet and counting people, say, in an hour. So sits there and counts people. How many are going to the toilet? If we look at the last one, it could be that nobody needs the loo in this hour, or it could be that loads and loads and loads of people are using the loo. Probably not in, bless you, probably not an infinite number of people, but quite a lot of people. If it is a big Wetherspoon or something like that, then lots of people will go there. The rate needs to be homogeneous. Well, if we, for example, look at how many people will use the toilet on a Friday night, say at 10 o'clock, that's a certain number. And again, if we look at how many people use the toilet on a Sunday morning at 3 o'clock in the morning, when the pub is closed. Well, you can't compare that because the rates are not homogeneous. When the pub is closed, nobody definitely will use the toilet because there's nobody there. So therefore, we need to make sure that we look at the rates at least during opening hours. Otherwise, it would be unfair. No two events must occur at the same time, because the poor person who is taking the records would not be able to record people if all of a sudden 5, 6 people at the same time go through the door. They can't do that. So they have to go through the door one after the other. Can't be exactly at the same time. Otherwise, it would not follow Poisson. And events must be independent. And that is where this example with the toilet and the pub actually falls down. Because I can only speak from my own experience. Sometimes the events are not independent. And it appears to me, as an outsider, that this is a little bit gender specific. Because my observation is, not that I've done this experiment very often, because I usually don't loiter in front of pub toilets, but my experience is that very often for female, this assumption doesn't hold. Usually, or very often, you see that there are, I don't know what the technical term is, flocks, groups, herds, prides, yeah. You can also say that for, what's the expression for badgers? Badgers. Don't Google it. What is a group of badgers? No, it's a confusion. So a confusion of females. Sorry, that was me, right? So ladies very often go in pulks, right? And it is sort of, I have no idea what they do, but I assume it is not just, it is probably discussing the latest boyfriend issues and things like that, right? So you see a whole group of ladies moving at the same time into the. So in this case, it is sort of, one girl says to a friend, "Hey, shall we go to the toilet?" And and the friend says, yeah, I need to tell you about that. And he's a total ass. And then another one, yeah, I know, I did that as well, and things like that. So so the events are not independent. My experience with males is it's more likely to be independent, because if you say to your mate from the rugby team, shall we go to the toilet? And they probably all look at you and say, if you want to, we can come with you, but what the hell are we supposed to do? So that gives you an idea what we mean by independent events and so on and so forth. No two events can happen at the same time and things like that. And what we can do with such a Poisson distributed counts is we can actually calculate another example for typical Poisson distributed counts. I forgot one. Relatively rare. So they don't happen very often, events. And a typical situation for that would be not just counts. It could be, for example, epileptic seizures in a given time frame, in a day or in a week or something like that. Yeah, that's another very typical scenario, which you will probably encounter in your assessment. And what we can do is we can calculate 95% confidence intervals. We can, of course, calculate sort of the average when we say, okay, we have, let's say, 5 seizures in a week, and then we have 10 seizures in a week. So we can calculate the average. We can calculate the standard deviation. We just simply compare the same time period every time. We have to have the same time period every time to make these comparisons. So a week or a day or an hour, or the same space, a Petri dish with the same surface area, something like that. And we can calculate counts, the average of these counts. We can also do standard deviation. We can calculate the variance in exactly the same way, although sometimes it will give a rather strange result, which we sort of would not necessarily expect from count data. We might find that on average, 4.3 people go to the toilet in an hour. And that's the average, and that will be over the in the long run, basically. Doesn't mean that 4.3 people go to the toilet, because that's not possible. Yeah, but in the long run, and this Poisson distribution allows us to make a judgment in the long run how this actually works. So we can calculate 95% confidence interval. We can also actually compare counts. So we could, for example, say we have some patients where we compare the number of seizures per week. So we might have without a drug and with a drug. And what we find is that we measure seizures per day, let's say, and we have 4, 3, 7, and here we've got 1, 2, and maybe 2 or something like that. And in patients, a very small group, so we can easily compare and say, does the drug actually have an effect? Yeah. And the tools are pretty much the same that we have used, although it's a slightly different way of testing. We have to formulate different null hypotheses. We have to do a different test statistics. We have to use a different distribution. And unfortunately, the Poisson distribution is a little bit naughty because it is not like the normal distribution. The normal distribution is lovely, symmetrical, beautiful. But the Poisson distribution actually depends on the rate that we are looking at. So if we've got a rate of 1, so rate of 1, and that is usually abbreviated rate with the Greek letter lambda. So that's lambda. Why? I have absolutely no idea. So lambda, that's the rate. And the distribution for the Poisson distribution would look a little bit like almost like a ski slope, where we have here the counts, and here would be a probability. So that means most of the events will be here at 1, and it becomes less and less likely that we see higher numbers. So here, the probability of seeing 10 is relatively low, but it is still possible. Yeah? And with the best will in the world, this is not symmetrical. Now, the Poisson distribution for, say, lambda equals 10 would actually look a little bit like that, with a maximum at 10. So this distribution is a, if you like, is a shapeshifter, and that causes quite a bit of, God damn it. Why does it have to shift shape, please? It's not fair. Okay, so how do we, for example, calculate remove that. How do we calculate a 95% confidence interval? 95% confidence interval. You would be tempted to say, well, we just simply take the measurement, our measurements, measure the rate for our sample that we have taken. So we take lambda and say this lambda that we observe is also the lambda that we would see in the long run. So if we see on average 5 seizures per day from our observations, then we would say, yeah, that is probably what we would expect in the long run, 5 seizures there.
Lambda's just given to the rate then.
That is the rate.
Right.
Lambda is actually the abbreviation for the rate. Yes, sorry, I should have made that clearer. No. But we can't be absolutely sure, so we have to say there is a margin of error in it, like we have done with the continuous data. Only problem is, because the Poisson distribution is not symmetrical, we cannot write lambda plus minus, say, a 95% margin of error. That's not possible because the distribution is not symmetrical. That only works if the distribution was like the normal distribution, nicely distributed. So unfortunately, we cannot just simply use what we have learned for the continuous data, how we do that. And in fact, calculating this confidence interval is, you can do it by hand. Excel can do it, but the equation is, the formula is a little bit involved. Let's put it this way. But luckily, thank God for that, we can use our trusted online calculator that I showed you. And again, use this calculator for everything that you do. And this time, what you want to do is you actually want to go to the tab called Count Data. It tells you that here. And what you get is this start page. Let's take this away for a moment. Because that's just a nuisance. And let's say we have, in this case, 20 events in a day, for example, seizures. We could say we might have, yeah, let's say 20 events in a day that we observe. And this calculator will immediately give you the upper and the lower bound, the 95% confidence interval. So here is the confidence interval. So in the long run, we would be fairly certain that the true rate is actually somewhere between 12.2 and 30.9 of seizures a day. Somewhere in between, we would be pretty confident with that. Yeah? What if, and what you see here, we measured 20, and this confidence interval, 12.2 to 30.9, 20 is not in the middle of it. It's slightly skewed, but that is a property of the Poisson distribution. So that's why this calculator is incredibly useful, because it immediately gives you the confidence interval without having to fuss around with a lot of weird and wonderful calculations. Now, if we get more information about what's happening, we said we can make the confidence interval smaller because we've got more information. So let's see what would happen if we keep exactly the same rate, but have the observations over a longer time period. Let's say we don't do it just for one day. We observe that person, or let's say we observe that person over 5 days. I use exactly the same rate over 5 days. So we would have, say, 100 seizures over 5 days. That's exactly the same as 20 per 1. Yeah. And we said, because we've got more information about the system, probably our confidence interval would be smaller. We don't have to look at a very wide uncertainty. We have more information and our uncertainty becomes smaller. And if you calculate that, what you see is that the same rate, but over more observations, you find the confidence interval goes from 12.2 to 16.3 and from 30.9 to 24.3. So the confidence interval shrinks. And what you also see is that it becomes more symmetrical. We have still 20 in between, but 20 is now more towards the middle of it. So it becomes more symmetrical. And in fact, if you've got large numbers, the Poisson distribution will become very similar to the normal distribution. But for small numbers, it stays rather skewed. Yeah? So this is how we can use this calculator for calculating or finding the confidence intervals. As I said earlier, we can also use the Poisson distribution to check whether two samples have the same rates. And for that, what we simply do is we use the concepts that we have learned for the continuous data. And we say, we want to know if, for example, 20 seizures a day in the long run is similar to 25. I can also do that, with larger numbers or something like that. So how would we go about? We would start with a protocol. Where is our protocol? So we would formulate a null and an alternative hypothesis. The null hypothesis would be there is no difference between the two population rates. We are not looking at the means, we are now looking at the rates. any differences between the two samples can be attributed, can be explained by sampling error only. Alternative hypothesis, there is a difference between the two population rates. And this difference cannot be attributed by sampling error only. There is actually an effect. Next step, we set the significance level alpha. As per usual, we would probably choose 0.05, 5%. And we would formulate our decision rules. If P is low, H naught must go. If P is high, H naught can stay. And then we will find the p-value, the probability, by calculating a test score. In this case, it would be, it's not called a Poisson score. It's probably called chi-square score, but you know, let's not worry about that. Let's just simply call it a test score. From this test score, we get this p-value. The p-value is the probability that we observe the calculated test score, or an even more extreme one, given that we believe that the null hypothesis is safe. It's exactly the same. It's terribly boring, I know, but you know, you don't have to learn anything new. And we compare the p-value, and based on that and our decision rules in 3, we say, yes, we reject the null hypothesis, or we fail to reject the null hypothesis. So now let's say we had, I don't know, we had 25 seizures in one day. And we want to know whether this rate in the long run is similar to, let's say, we have 40 seizures in 2 days. Yeah, to mix that up a little bit. What do you think? Is it the same?
No.
No? So 25, 40, that would be 20. So that's the second one is a little bit lower, isn't it? Yeah. Okay, let's see what our calculator says, because we can do that with the calculator. So we have, what did I say? 25 in one day. And we had 40 in 2 days. Yeah. Here we've got our confidence intervals. Sorry? They're different. Are they different? Do they overlap?
Yeah.
Yeah. So if they overlap, remember what we said, they could be, or they might not be, indicative that there is a difference. So with overlapping confidence intervals, we basically, we don't know really. But luckily, this gives us a p-value. So the p-value is 0.45. P, is it higher or lower than alpha? Alpha was 5%.
Sorry, higher.
It's higher. Yes, absolutely. 0.45 is higher than 0.05. What did I say? 0.45 is higher than 0.05. Yes, that is 45% compared to 5%. P is high. What does happen to the null hypothesis? It stays. So we say there is no difference between the seizure rates. Not that we can actually tell. It might be a difference, but we don't have any evidence for that. Yeah. So your gut feeling, unfortunately, was not right. Yeah. Because that is what the p-value actually tells us in this case. Does that make sense? Yeah. Happy with that? And you probably will be delighted that you don't have to do any calculations with that. You just use the online calculator, or you use the advanced calculators on my website, which do exactly the same thing. There are a few more restrictions when you can actually use the Poisson distribution and when not. But for our purposes at the moment, we just leave it like that and say Poisson when we have count data, when we measure rates. And very often for example, in the lab, when people do experiments with bacteria or something like that, I don't think have you done things like that where you grow bacteria colonies or something like that? No? Oh, you don't have labs. Oh.
In theory.
Well, but you can imagine that people grow bacteria and they spread colonies and things like that. And for example, you can very easily think of an experiment where people are looking for new antibiotics. So we test a previous antibiotic and measure how many colonies of bacteria grow on the old antibiotic. Then we change the formulation of that and measure, do more cells grow or do less cells grow when we change the formulation. And that would be, again, another very nice example for the application of a Poisson, because bacteria cannot grow at the same time, so it's independent. Not two can happen at the same time. It is independent because the bacteria that are grown on one plate don't know of the bacteria on the other plate, so it's totally independent. And it can be basically from 0 to God knows how many. So, and it's not that common observation unless you've got loads and loads, millions of bacteria on it, but then you just simply dilute it. So it's a really nice way of being able to compare these rates with each other. And it's a very common task that from our biostatistician to do exactly these comparisons and to give these confidence intervals. Make sense?
Yes.
I suggest we have a 10-minute break, and then the last act with count data, no, for today, we are looking at proportions. Yeah? Back in 10.
Thank you.
Make sense? Still? Good.
Okay, well, I'm just going to take Can you not take that one to take it? Oh, and explain what's making this difficult.
Yeah, you can. Actually, it's a pen.
No, just put it in.
No, it's actually a silence.
Oh my God. What do you have?
16.
That's fine. Is anyone else sort of, I suppose to do I can't.
This is being recorded,
Yeah.
Oh, yeah, yeah, yeah. Please don't be in pain.
I'm hitting a quick well. I don't know if I can.
If there's anything that you can do, go home or, lie down somewhere, please.
Yeah, it's just frustrating because obviously I probably won't want to be here and everything, but I'm just, I'm hitting my
It's
limit.
recorded and I've put already all the recordings so far on the website.
Okay.
So it's all there.
I'm not sure about the next session though, so I'm not sure if Kirsty's session's recorded, because that's in the
Jeez,
computer
yeah.
lab. So, are you on campus or are you?
No, I'm at the hotel.
Okay. What helps?
And standing up,
Stand up if you want to.
yeah.
What I can do. There's a standing desk here if you want to use it.
Oh, really?
Yeah.
I feel awful to push you off it though.
It's fine. I'll stand up with you.
Hey, okay.
I've got a standing desk at home. If that's
I
okay.
stand up.
Let's do that. I'll stand up.
It's just because I've got podiatric cysts and everything, I've got an impinged nerve in like a bone spur, so the longer I'm sitting, even though I keep getting, I'm so grateful for the breaks, but it builds up throughout the day, so there's a point where you can stand and then sitting back down, it's hit limit of like improvement.
Yeah. Well, stand up with me. This is taking forever. I've got a button at home that I press.
Yeah,
Thank you.
There you go, very much.
I'm assuming that's what this is for. So,
No, it helps with the ironing.
we give, obviously it's not my company anymore, we give standing desks to everyone as standard at home because I like standing up, therefore I enforce it on other people. You know, but you get the option of standing or sitting.
Can I optionally, can I use a hammock?
Hammock, yeah, go for it.
I used to sleep in a hammock because it helped, because there's no strain then on the back
Yeah,
whatsoever,
yeah,
it was amazing.
Yeah.
I'll go put, I even now, I borrow it every day downstairs.
So they have another session after that.
They do today, yeah, they've got gene analysis and data presentation. I don't know, so I haven't got the room on my agenda. So I don't know where it is, but I know it's not here, so I'm hoping
Gene
it's
analysis.
about 4:15.
PC2.
Is it?
Yeah, I think it's downstairs. I'm not sure. It's this building.
Kennedy, PC.
It just says PC2, but I'm assuming it's this one.
At 4:15.
Yeah.
God damn it.
Until 5.
Because I thought the next one we just do in 20 minutes.
That's right.
And then you have the rest of the afternoon free, but I'm so sorry.
It's not your fault, it's Kirsty's fault, she put it in. Kirsty might, you never know, she might be around earlier as well.
How are you probably asked you that, how are you with logarithms?
You asked us this morning.
I know.
I'm okay.
You're okay.
No.
Mm-mm.
No.
Logarithms? No.
No.
Work of the devil.
Yes.
Okay, good. Good. Logarithms?
They're okay.
Yeah, okay.
Yeah.
Hmm. What am I going to do? I need to be creative because we need logarithms tomorrow. I will do a quick refresher.
Maybe if the session is only going to take 20 minutes, we've got until 4:15.
Oh yeah, I can do the logarithms now then.
If you want to
Take a tiny introduction.
Sorry?
intro,
Yeah, like an intro.
Yeah? A little
we
bit?
have the time if you do.
Yeah.
Okay, yeah, fine, absolutely, then I don't need to worry about it. Yeah, good point, good point. And what is your timetable tomorrow? So we've got 9 to
9 to 11 with you, then an early lunch from 11 to 12, then 12 till 2 with you, and then 2 till 3 Kirsty's like rounding up and saying hi.
oh, I see. And then you can do the assignment with
Yeah, the exam, there's a deadline on the 29th of this month for the quiz. The assignment is because it's a project, I think they said it's kind of whenever.
fantastic. Okay. Okay.
Yeah.
How many guys do we have? 4.
Guys, like,
Men.
yeah.
Gentlemen, 4. 4.
My department is, but that's because it's mainly admin. It's just filing and saying, yeah, that's, but then the other jobs that are like on sites are still anyway.
Really? Why was Sophie my dominator? Oh yeah, this is the recipe.
Well, I don't like, I'm allergic to banana.
Allergic?
Yeah.
How do you live?
I just don't eat banana.
You are allergic to?
Bananas. She showed me a recipe for like a banana muffin, but I'm allergic to bananas.
There's stuff with something.
I'm going to make them when I get home.
Is that butter?
That's just butter.
Ah, okay.
Well, I think it's weird to put butter on muffins.
Mm.
But the other one, I was either going to make those or these, but these don't have very good meats.
I like banana, blueberry muffin.
Yeah, I like you think the muffins on here don't seem to be that good. Not a bit different.
No, they have like blueberry muffin cake.
At that point, how do you make a muffin cake? Is it not just a cake or a muffin? Yeah, big.
And we just had that, oh, this was thinking, we were really say crumb cake.
Have you had the Gales one?
No. The Gales are used to it. But it's so expensive stuff.
Yeah, it is expensive. I said that at the gym.
When we get out and get free coffee. So I keep signing up.
Yeah. Really? I only know.
We need different emails for this.
I think so.
Yeah. How many emails do you have? Okay. There's some for so many things. I have an official email and then I do one email.
It looks fun. Oh, okay. Trying to see it. Oh, yes.
Okay, we get to
Yeah,
the back.
it was
Good.
like
Really good concept.
but I always just use that.
Careful, don't fall on the cake.
Yeah.
Yeah, mix it up a bit.
If we go to the library getting books, we can make all of these standing desks. I've never actually, because we've got standing desks at the office, I've never used it.
Oh, I've used it quite a few times. Yeah.
Does it feel really weird?
No, it feels pretty good. My brother had it at his office, and then now he specifically wants to desk at home now.
You probably have got like walking patterns. I see that people.
Some
standing
have
desks.
walking plans.
I'm so used to.
Oh.
You buy it and then you use it for first week and then when we meet
That would be good. With like a desk that comes out from you, so you can just swing, but it's still in place.
Well, what you need, there's a sort of the screen up there.
Eventually, we'll be working in like virtual reality, won't we? Like VR headsets on. Oh wow, VR headsets just like a I love it. My mate's got a game.
Only if that benefits the fact that.
Plays and swords. And you literally just go into it, like essentially like a plan.
Where is she? I will just check on the middle though, that I've got the right.
I hate that. That was nice.
Oh, right, yeah. One thing, 5 nights of Freddy's VR.
I don't know, that's not
I don't really play horror games in general because I don't.
loud now, like you want to stand and immediately start
The
spawning.
VR 5 nights of Freddy's.
I did that, I realised it was. I'm working on the live.
Let me look at the cameras and see. Look at the cameras and then you
Electricians.
Yeah.
I don't like embellishment styles. I also like that's what I go for the course. I'm so angry at the course because you can't see development. Yeah. So I just asked it, so like it's
Sometimes they give you
It just makes you realise that they do just do it better in America.
I think they do it.
Yeah, I just think
Americans in general do just do bad. I don't feel bad about it. The pressure to spend $100 on your.
I mean, to be honest, I spent that on support.
Okay, we are getting back to being quorate. Yep. Excellent. So last push. Last push before at least I disappear. So we looked at the rates And there's typically these count data, as I said, and you immediately see that, and from the context, you understand that these are discrete data, right, for the Poisson distributed data. There is another type of count data where it's not so obvious that these are discrete data, because what could happen is that, of course, numbers with decimal points could appear. And that is when we are working with proportions. Just imagine we are looking at, and proportions are defined as so a proportion is defined as the number of, people call it successes, divided by the total number of trials. That means, in this case, success plus failure. And you shouldn't see that as a sort of something with a particular value attached. A success could easily be that a person dies. Yeah, and obviously from that person's perspective, success, with me being dead, I wouldn't classify that as a success, but we see it like that. So it could be, for example, number of people for whom the treatment worked over the number of people who actually enrolled in the entire process. That would be a simple proportion. Proportions, from a statistical point of view, are a total pig to work with, because unlike continuous data, and to a certain degree Poisson data, proportions are double bound. You cannot have something smaller than 0%, and you can't have something higher than 100%. You cannot have more people benefiting from the drug than actually were enrolled on the program. That's not possible. So therefore, you've got these boundaries, 0 and, if you like, 1, if you express 100% as 1. But you can easily have decimal points in it, so in a way fractions, and it might appear that a proportion looks like a continuous number. So, for example, you have 10 people benefit from the drug, that these are the successes, and you've got 30 enrolled, so you have a success, bless you, you have a success of 33.3% or 0.33, which looks like a continuous number, but actually it isn't, because it is a sort of a composite of two count numbers, if you like. And of course, you could do exactly the same what we have done before. You can say, right, I measure the proportion of something happening from a sample, and then try to infer what would be the proportion in the population. But of course, I don't know that exactly. So therefore, I have to express it again as a proportion plus or minus some margin of error. And as we said, we probably need to be a little bit careful, because we've seen with the Poisson distribution that it might not be symmetrical. I think in this case it is symmetrical, but just be on the safe side. So all we need to do is find the confidence interval of something like that, and use this confidence interval then as a sort of an estimator what it will be in the population. So what we could do, for example, is, and I hope I'm not politically totally incorrect, I noticed we have 17 participants, 4 of which I consider male. If you disagree with me, please feel free to shout. But I think that we've got 4 male participants, so we can calculate our sample proportion, and then try to figure out the proportion in the population. But we need to be careful with the population in this case, because what would be our population? It would be probably not the population of all students at the university. It might be the population of apprentices participating in the clinical trials apprenticeships. Yeah. So we need to be very careful, especially when we work with proportions. So we can calculate that. In this case, our sample has 4 in a total of 17. Yeah. And I can't do that in my head. So 4 divided by 17 equals 23.5%. So equals 0.235 equals 23.5%. Yeah. Helen, you said something yesterday in terms of your observation at sort of this level. What is the percentage of males or females?
I think 80% female.
80% female. Aha. So that would mean 20% male. Well, it's probably, yeah, sounds about right, doesn't it? Yeah. Okay. So how do we find now really the population proportion? Again, we go with our sample and say the sample proportion is the best estimate that we have. And we now need to find the 95% confidence interval for that. And guess what we are going to use? Our online calculator, because it can do that. So online calculator. But now you need to go to the tab that is called chi-squared test. And I know that some people have PTSD when they hear chi-squared. And the reason for using this chi-squared is because this proportion actually can be modeled by this chi-squared distribution. Again, the chi-squared distribution is not a symmetrical distribution, and it's a little bit like the Poisson distribution, looks also a little bit like the Poisson distribution. And for very large numbers, we have big numbers, although the proportion is still below 1, it will again look like a normal distribution. So what we can do is we can now try and calculate our proportion. I take this away here for a moment. So we said we have 4 male participants in a total of 17. And we get a confidence interval between 9.6% and 47.3%. So our best estimate is that when I look at the proportion of males in the entire population of clinical trials apprentices, the true proportion will be somewhere between 9.6 and 47.3. It's a huge confidence interval, which is due to the fact that the numbers are fairly small. Yeah. So we can get this confidence interval. Now, what would happen, just from your intuition, what would happen if I make the numbers much, much larger? What would happen to the confidence interval, making the numbers larger but keep the proportion exactly the same? Smaller confidence? Shall we try that? See whether you're right? Okay, good. Let's say we multiply everything by 100. Okay. And you were absolutely right. Between 21.6 and 25.6. So much, much smaller. Yeah. And our 23.5 is probably pretty much in the middle of that. That is why when you have large numbers, the confidence interval shrinks. We are far more confident about the numbers because we've got more information about the population. A word of caution. What you cannot do with proportions, so here, yeah, we've got wide confidence interval. I probably should write that down. 95%. CI was from 9 to, what was it, 47 or something like that percent. What you need for this calculation is actually the raw data, which means you need to have the number of successes and the number of totals. If I say to you the proportion is in the population, we have, say, 23% male apprentices, this number, this 23%, is totally useless for this calculation because it already gives you the ratio, but it does not give you the total numbers, and you have seen it depends on the total numbers. Yeah. So I had the task a while ago to look at sort of approval rates, and people gave me a list and said, well, Last year we had an approval rate of 78%, and the year before we had an approval rate of 85%. So we went from 85 to 78%, disaster. And I said, no, you can't really say that, because you just have the percentages, but I could be very well within the confidence intervals, yeah? And we need the raw data. And then they said, we don't have the raw data. And I said, then you can't say anything. End of discussion, let's go to the pub. So, seems to be a theme with me, right? Haven't been to the pub for ages, I want to say. Okay, so this is how you can get these confidence intervals for proportions with this online calculator. And of course, we can also test whether two proportions are actually from the same population. Guess what? It's exactly the same old chestnut again. We do exactly the same what we have done before. We do our protocol. And all we need to do is we need to change one word. So we formulate our null and the alternative hypothesis. For the null hypothesis, there is no difference between the two population proportions. And again, we are not looking at the sample, we are looking at the population proportions. Any differences that we see in the sample proportions can be explained by sampling error only. I told you, it's absolutely boring. Alternative hypothesis, there is a difference between the two population proportions. Any differences that we see in the sample proportions can no longer be explained by sampling error. There must be an additional effect in it. We set the significance level alpha, usually 5%. We formulate our decision rules. And if P is low, H naught can go or must go. If P is high, H naught can stay. We calculate the p-value and then make the decision. How do we calculate the p-value? The p-value in this case is calculated from a test statistic. This time it's a chi-square statistic, but don't stress about it. We will come to that, how we do that. And eventually we come to a conclusion. So let's say we do a comparison between the clinical trials apprentices. And since I've got you here, we have four male out of 17. So that's the clinical trials. If we did the, say, a psychology apprentice, no, psychology is bad. Engineering apprenticeship, yeah? We would probably get, I would guess for electrical engineering, roughly, sorry?
One of my mates, he does electrical engineering, 250 people in his class, there's 2 women.
2?
250.
Okay, yeah, okay, we can ask the question. 2, no, so we have 250, so we have 248 out of 250 are male, yeah? Is that right? Because we can only compare the same things. Would be, I think that is quite dramatic. it's actually interesting because I've worked a while in Malaysia, and at an university that's specialized in engineering. And interesting observation, and I fully agree, you know, in the UK, engineering is predominantly male. In Malaysia, I would say it's about 50-50. That about 50% of participants are female, actually. And when you look at building sites and things like that, you will find very often female engineers in fairly high positions in Malaysia. So they are probably a little bit more, they are a bit less gender restricted, let's put it this way, which you didn't necessarily expect at that point. Okay, let's compare that. How we are going to do this? Well, we go back to our calculator. We have 4 out of 17. And what did we have? 248. 248 out of 250. And we get confidence interval. It goes from 97 to 99.8%, right? And I think you don't need to really be a highly trained statistician to anticipate that we probably can reject our null hypothesis. Yeah, let's see what the p-value is. Well, the p-value, and that's quite good that we chosen that. The p-value is, we don't know exactly. It is really, really small. It is smaller than 0.001. And usually, if your p-value is really small, you wouldn't write this as p-value is 5 times 10 to the minus 6 or something like that. You would just simply indicate it as p smaller than 0.001. And you see that very commonly written. So p is low. I think it is safe for us to reject the null hypothesis and say the two proportions are most likely not the same. Yeah, makes sense? So we can note that here. P is smaller than 0.001. That means our null hypothesis is rejected. Yeah? A slight word of warning, though, and that is these calculations that this calculator does are usually, and this chi-square approximation is usually pretty accurate between, let's say, 20% and, say, 80%. So in this range, the calculations are absolutely fine. If you go smaller than 20% or above 80%, you need to be careful with that because it gets less and less accurate. But I think in our case, where we have something between, what was it, 96 and 99 point something percent, we probably can assume that, you know, we don't need to worry about that. If you are frequently working with very small or very large proportions, then it is usually what people do is they do some transformations. As I told you with the log transformation earlier, these transformations can get pretty wild. You would normally just, it probably doesn't mean a lot to you. In a case like that, you would perform an arcsine transformation, whatever this is. A calculator will do it, so don't worry about it. And in a way, you don't need to worry about it as well. One thing that you need to worry about when you perform these proportions is, so caveat, one caveat is that the sample that you take, so for example, the 17 participants here, the sample must be much smaller than the total proportion, than the total population. So if I, for example, say the total population of clinical trials apprentices in the entire country is, let's say, 20 participants, and we've got 17 of these 20 participants sitting here, and 4 of them are male, then this sort of, the stipulation, this rule is broken, and you can't really make an educated guess what it would be in the population, because the sample is not much smaller than the population. It usually, bless you, usually the rule is it must be smaller than 10% of the population. And one last thought about the issue that I raised earlier, and which you correctly identified. If we take larger numbers, same proportion but larger numbers change the result. You are actually victims of that, because when was it? 10 years ago. When was the Brexit vote?
2016.
16?
Yeah.
9 years ago then. 9 years ago. When the then Prime Minister David Cameron sort of decided that it would be a good idea to do a vote on Brexit, what he basically did was he asked a few people and said, and asked them, would you vote for Brexit? And they all said, hell no. A, it was not a representative sample. B, it was a small number. And that small number was sort of fairly below what the the true population proportion actually would have been. And he thought, okay, everybody says no, we don't vote for Brexit. It's a crazy idea. So he said, okay, good. So it's safe to do that. So we set up the referendum, and very much to his surprise and his dismay, the numbers started to come in and the proportions changed, because he relied on small numbers of non-representative sample. And that was a huge mistake. So the take-home message from that really is when we are working with proportions, we need to be very careful. We need to make sure that it is indeed representative, that we are not just working with percentages, that we are working with confidence intervals, and that we are working with raw data from these confidence intervals. Make sense? I thought that I get started with the next topic then, where we look at combinations of things. But I think everybody is a little bit tired. I know you've got another session. So, today? What's that?
It's my fault for not checking the agenda. I didn't realise we had another session.
You do, don't you?
Yeah. Apparently, what is the next session?
We're in a room downstairs, I think. We're not here.
Okay. Oh, that would be interesting. Let's see if you can apply something of this. Do they do some statistics in their data presentation and gene analysis?
No, they're going to have a hypothesis, but
Sorry?
I just know it's mainly they'll have a hypothesis they'll be investigating, but that'll be.
Okay, so no numbers. Do you want them now?
Yeah. Yeah. I mean, have a
break, and then we continue tomorro 'Q with what probably gives you PTSD, proper chi-square tests. Yay! Yay! You have done chi-square tests, haven't you? A-levels. Have you done chi-square tests? What? You have. Fantastic. Well, then we can whiz through it. Okay. Thank you very much. See you tomorrow and enjoy. Thank you very much again for Angela's stuff. She will contact you. Absolutely. That's why I married her.